So I want to start today by setting up a conundrum that people interested in understanding and verifying the behavior of software find themselves in pretty often. So let's say that we're looking at a large code base of relatively low-level code. To make this concrete, let's say that we're talking about the reference implementation of the Python programming language, the CPython interpreter. For many reasons, it might be useful to have a high-level description of how this code base works and have confidence that the description is up-to-date and accurate. Ideally, we'd like the effort of creating and fact-checking that description to be automated so that changing the code does not undo all of the effort that was put into describing it. Unfortunately, we can't achieve this by writing natural language documentation because it's not precise enough for us to automatically detect if or when changes to the code render it inaccurate. So we won't get anywhere by just using informal language. What about formal language? Those in the room familiar with current software verification approaches may now recognize this as the point where we ask the dreaded question, what's the specification? A specification is a prescriptive statement of what we, or rather representatives of the relevant community of users, think that the code should do. In safety-critical contexts like aerospace or defense, the community of users is willing to invest in maintaining a detailed prescriptive statement of how code is supposed to work. The rocket scientists are willing to go to the trouble to tell us exactly what the code written for them should or should not do. But do you know who's not a rocket scientist? We now live in an era where many people are open to, or even reliant on, the expectation that they can describe programmatic tasks to language models designed for open domain chat, and in response, receive code that meets their description. Language models have eliminated the bottleneck on producing roughly coherent text of all kinds, so much so that writing code is no longer the real limitation. We can now write code at the same speed that a language model can predict tokens, and we can prompt it by saying almost anything. The real holdup is in knowing whether we can trust what we've received in return. Python is the lingua franca of AI. This was true even before conversational AI systems were writing so much of it. But now, with increasing usage of language models as general-purpose agents, Python has become the default language for use behind the scenes to fulfill programmatic requests. In fulfilling these requests, the text that users provide while articulating their goals is not prescriptive. Being prescriptive is a responsibility. It means that you are assumed to know what you're asking for, and what you're asking for is what you expect. That is not a responsibility that the average ChatGPT user believes themselves to be taking on. Instead, the average user is simply making an attempt at articulating what it is they want to happen. They're proposing a description, which they expect to converse about so that they can explore whether that is what they really want. So if we were a conversational AI system trying to participate in that kind of conversation, we now have to account for and prevent two kinds of mistakes. One, I didn't know what the user was talking about. Two, the user didn't know what the user was talking about. The first mistake happens when the user knows the behavior they want, but they have prescriptive intent, but the system misinterpreted them. The second mistake happens when the user thinks that they know what they want, but the consequences of doing what they have asked for are not what they believe them to be. At this point, I'm going to introduce one massive simplification. Let's say that the user isn't just conjuring their request out of thin air. Let's say instead they're looking at a body of computer code. Well, keeping that code anonymous, that's why it's unreadably small. Let's further assume that the user is only interested in talking about behavior that code can be said to implement. And so there's a property P, and we only care about a property if it can be attached to this code base, so to speak. So now the user is still fundamentally in the position of trying to describe what it is that they want, but there's now an artifact visible to both them and the system that is supposed to align with their request. At this point, you may be thinking, didn't he just shift the goalposts by a lot? Is this even the same presentation? Let me argue that it is. What we've done is change the question from, does your statement mean X, to, is X, in this case, this code, what your statement means? One day, I would love it if language models were truly adapted to fill in X with something correct for any squishy, non-prescriptive natural language request. But first, we have to figure out what it sounds like to talk about requests whose meaning we do understand. Or another way of saying it is we have to understand how to ground meaning in artifacts that we can comprehend. In the bigger picture, the only difference between asking, does your statement mean X, and asking, is X what your statement means, is how good of a guess X happens to be. So in the long run, these two things would become the same. So let's say our X is a big pile of code from a large and broadly relevant code base like the CPython interpreter, and we are trying to begin our journey of understanding how to talk about the kinds of things that Python does. Well, if we're going to start off fully formal from the very beginning, the first question we'd have to ask is, what's supposed to happen here at the very end? We could then use a proof assistant to try to write down exactly what we think could have happened, and then go through the code step by step, showing that this is, in fact, exactly the set of outcomes that could have occurred. What I've just roughly described has had a name for half a century, articulating the strongest post condition. A post condition is basically what it sounds like. It is a mathematical description of what conditions should hold after the code has been executed. The strongest post condition is the specific mathematical description that captures every way that the code could possibly behave. It's an upper bound on possible behaviors of the code. But how likely is it that we want to know all of that, or that we want to have to come up with all of it? It's pretty unlikely. This is the root of why verification is hard and requires careful thought. You have to be picky about what you actually care about knowing when the program is done. Otherwise, you're going to make a whole lot of extra work for yourself. So the post condition we really want is almost certainly not the strongest one we could have. It's something more middling. But we're still looking at this big pile of code that we don't understand. So what is this magical middle ground that captures just the things we care about? Well, no decidable procedure can tell us that. So we're going to have to start guessing. Once you start guessing, there are two ways to guess wrong. You can create an over-specification, or you can create an under-specification. An over-specification is a statement of what the program does that includes too much. It includes behavior that isn't really there. In contrast, an under-specification is a statement that leaves things out. It only describes some of the behavior that's really there. One way we can get to an exact specification, something that's just right, is by first under-specifying and slowly adding more and more detail while making sure that we aren't adding anything wrong along the way. So let's look back at our big pile of code. Perhaps we don't know how to state the big post condition that goes at the very end, but what if we just zoom in on a bunch of little parts and try to get an understanding of what they do? Now, let's say that in each of these small areas, we are fine with producing an under-specification. So there's stuff going on in each of these regions that we're not going to try to explain. Whatever that stuff is, we're going to discard it. This and only this, P1, P2, P3, is the description of what's going on in those respective parts of the code. If something else is happening, no, it isn't. Now, for each of these regions, I can ask a very specific question that proof assistants are already very good at answering. In each of these regions, what has to be true at the beginning of them in order for the code in those regions to run and have at least P1, P2, and P3 be true, respectively, at the end of each of those segments? This concept is called the weakest precondition. Then we can ask another question the proof assistant is already pretty good at answering. Does the weakest precondition of P3 line up with the post condition we asserted at P2? And does the weakest precondition of P2 line up with the post condition we asserted with P1? This basically says if you think that you should have accomplished something, but you underspecified the previous code, so you can't possibly have done the preparatory work that you need to, then you know you found something inconsistent. So if these joints don't line up, then we have learned something. The high-level description we just attempted to give is not consistent with this code. even if we're willing to ignore most of what the code is actually doing. Upon seeing that this has happened, we don't have to take it as a tragedy. We can just say, I knew that P1, P2, and P3 were under specifications anyway. I just wasn't precise enough in identifying where exactly they did apply. So we can then go back to each of these smaller parts where we had zoomed in before and ask, what did I miss? What was I overly broad in characterizing? Now, rather than having to ask ourselves what is wrong with our prescriptive view of the code's behavior, we can just ask, how can I describe more of what I know is going on? Or do that more precisely. My underlying argument is that both of these tasks that I've described, checking whether an underspecification captures some behavior of a small region of code, and checking whether subsequent underspecifications are actually overspecifications relative to those preceding parts of the code. Both of these tasks are significantly easier to automate via heuristic proof search methods than the task of trying to do both in one single pass over the code, come up with an exact specification. This would make sense because both of these tasks are much more approximate. The stakes are much lower if you fail at these than if you have to go back and get a new consensus from the entire community of users as to what we should prescribe about how the code works. So what stands in the way of this approach? In reviewing the papers that follow, I attempt to provide evidence that there is nothing fundamental standing in the way of this approach, just the practical application of enough imagination, engineering, and follow-through. I hope to convince you with the 3 papers that I examine of this hypothesis as best I can, and also provide a review of what the papers were accomplishing on their own terms. So we start with the paper, Jiang et al. 2023, an analysis of the costs and benefits of autocomplete. So when most of us think of language models assisting programmers, we probably think of tools like Copilot. Many observers have noted the similarity between what language models are trained to do, provide a continuation of text, and what existing code editors are already trying to do for programmers with every word they type, autocompletion. It seems like a straightforward extension. The purpose of autocomplete is to save typing. Anyone who has experience with standard autocomplete knows that most of the time, the majority of suggestions are not relevant. So if autocomplete was simply better at guessing what it is we meant to type, would it not be much faster and more helpful? What if we could just describe in much more approximate, informal terms what it is we wanted to type without even using programming language syntax? Well, this is closely related to our original question about how to use language models to write code. It's not getting them to write it that's the problem. It's trusting what they give us in return. So we have 2 hypotheses. The bottleneck of autocomplete is in physically transmitting the programs that programmers already have formulated in their head into finger motions via the keyboard and therefore into a program file. Alternatively, the bottleneck of autocomplete is the programmer's knowledge of what the right program actually looks like. This knowledge is built by incrementally verifying the code as they compose it. That question is one we can actually get insight into by studying what exists now. And that's the purpose of this study. Jiang et al. Conducted a user study to assess how autocomplete affected a cohort of 32 students. They discarded the data of 5, ultimately, who had been asked to complete simple programming tasks using a novel API, the Java Gmail API. Participants were exposed to a modified IDE setting based on Visual Studio Code, which is depicted up here, in which half of their screen was taken up by an editor view, and the other half was taken up by a document view containing static documentation of the API. Participants were given 110 minutes to complete 10 coding tasks of increasing difficulty. Afterwards, they were given unlimited time to answer 24 quiz questions meant to assess their understanding, exploration, and memorization of the new API. The control group was given an IDE with autocomplete disabled. This meant that their only option for finding relevant information was to scroll through the documentation and other resources curated and displayed on the right-hand side of the screen. The treatment group was given an IDE with autocomplete enabled. Participants' activity would be categorized based on which areas of the screen they looked at during the 110-minute task completion period. At any time, if the participant was engaged and not on break, their gaze could be in three places: on the editor view, the documentation view, or the terminal view along the bottom, which takes equal real estate from both other views. If a participant was gazing at the page of static documentation or at the suggestion box or suggestion details during an active autocomplete session, that span of time was counted as documentation reading time. If their gaze was anywhere else within the editor, the left side of the screen, that was counted as coding time. If their gaze was in the terminal area, that was counted as terminal time. So how did autocomplete affect programmer performance? Well, according to a Wilcox and 2 sample test run on the number of tasks finished by treatment and control groups, the use of autocomplete did not have a statistically significant effect. Oh, sorry, this is a more detailed view of the autocomplete. Did not have a statistically significant effect on the number of tasks that participants completed. Basically, there's an 11% chance that this experiment provides evidence for a significant difference in the number of tasks that anyone actually was able to solve. However, a linear model, they didn't say exactly which, probably a linear mixed effects model, found a significant difference across treatment conditions. That p-value was, I think, 0.01%. And parameter estimation from that model revealed that autocomplete contributes a speed up of about 8.2% of the time it originally took to complete the task. Where did programmers make up this time? Their analysis shows that most of it came from reductions in documentation reading time. By running one-way analyses of variance, or ANOVA, Jiang et al. Found with a p-value of 0.01 that participants with autocomplete spent 18 fewer minutes on average reading documentation than participants that did have access to autocomplete. Sorry, these are slightly out of order. The standard deviation in both groups was about 2.5 minutes. This turned out to be a statistical test with a very large effect size. The two groups also spent slightly different amounts of time coding. As mentioned here, on average, autocomplete users spent 46 minutes coding versus 52, but it was unlikely, as you can see, according to this p-value, that these were truly distinct means for these groups. How could it be that autocomplete did not reduce coding time? Well, as it turns out, autocomplete very much did not have a significant effect on the mean number of keystrokes typed by both groups. The F statistic, the ratio of intragroup variance to intergroup variance that they show here, is quite minuscule. The effect size, which is the D statistic there, corresponds to a small effect size. And the likelihood that the means are indistinct is 65%, so very high. So this suggests that programmers made up the keystrokes that they saved by accepting autocomplete suggestions in one of two ways, either by deleting all of or part of the suggestion after they accepted it, changing their mind, or by aborting the autocomplete session without accepting anything. So using it to explore the space of possibilities, but ultimately not accepting any of the suggestions. In their most unexpected result, Jiang et al. Found that contrary to their expectations, autocomplete users actually performed better on the post-programming quiz. They found a large and statistically significant positive effect of autocomplete on quiz score, raising total quiz points from 32 to 38. Each group's score had a standard deviation of 1.3. Yes, and I believe the p-value for this was very low. I'm forgetting exactly what it is. When broken down by understanding, exploration, and memorization-oriented questions, a statistically significant difference was observed for questions relating to understanding and exploration, but not for memorization. To contextualize these results, it helps to break down the mechanisms by which autocomplete can affect programmers. Autocomplete can function as a more ergonomic kind of search bar. Well, you would have to leave the editor view to do a word search in the documentation. Autocomplete searches the documentation without you having to leave the position in the document where you were already working. But unlike word search in the documentation, autocomplete also applies certain semantic criteria to ensure that the type of the symbol it is offering as a completion is valid at that point in the program. The differences documented by Jiang et al. Could be explained as purely the effect of the ergonomic advantage, but it doesn't seem obvious why this alone would cause such a notable difference in the degree of understanding and exploration of the API between the two groups. So in summary, Jiang et al. Provide compelling evidence that autocomplete helps programmers code faster by offering more semantically targeted forms of documentation than can be provided by a static document. It's the elimination of categorically inappropriate options that helps the programmer complete their task more quickly. This process of elimination isn't necessarily helped by receiving a good singular guess of what the programmer meant to write. In fact, providing a guess could be distracting because it shifts the programmer's mindset from weighing all options to proving or disproving whether a specific choice is appropriate. If this understanding is correct, then the real limitation that prevents us from allowing our IDEs to do more of our typing for us is in our natural language understanding of the code that programmers seek to extend or modify. A description of the programmer's understanding of the code base is the real Rosetta Stone we need to decipher the decisions they are weighing and the constraints they are trying to satisfy as they type. It is worth asking, then, to what degree do language models innately understand those kinds of logical descriptions? Wu et al. Investigate a problem known as auto-formalization.
Sorry, can I ask a quick question before I move on to the next one?
Yeah, go ahead.
So is the conclusions you just gave about sort of what function autocomplete is playing for programmers, is
Mhm.
your conclusion from the paper, or is that the author's conclusion?
It's definitely my interpretation top the results that they're giving. Yeah,
Okay, thanks.
those statements are not in the paper.
Sure. And did they have anything to say on that subject in the paper, or were they looking at other aspects?
They're sort of what they went into the paper trying to either prove or disprove. Um, it seems that they were mainly interested in it from a learning research perspective, and they thought that autocomplete might impede learning because they sort of had the underlying hypothesis that if it helps people guess what to type without knowing why they should type it, then maybe it shouldn't be used in learning environments. And so what I can infer about their intentions was that they meant to set this up as kind of a test of, will students learn more if we do or don't give them a lab assignment to do, where they either have to go find the answers themselves completely from the documentation, or they have this way of, accessing the documentation that's a bit faster and more intimate.
Okay, thanks.
Yeah, thank you. Yeah. So Wu et al. Ask, given a statement in informal language of some mathematical truth, to what extent can a language model automatically translate this into a formal and mechanically verifiable statement? Wu et al.'s problem setting is not exactly the same as ours. Rather than examining informal statements about the logical states of programs, they investigate informal statements of mathematical results. Because mathematics is an enterprise belonging to all of humanity, it is a much wider domain that encompasses a much broader set of statements than a typical program logic. In a sense, this makes autoformalization of mathematical theorems a lower bar than autoformalization of accurate descriptions of specific computer programs. In general, there are even fewer formal proofs in the world than there are informal proofs. Compared to the scale of data that language models ingest during pre-training, the number of parallel examples of formal and informal statements of theorems of any kind is probably somewhere between marginal and non-existent. So we might ask, is it delusional to think that language models can relate informal logical statements to formal ones? Wu et al. Show that the answer is no. They apply the Codex language model to 150 problems from the math dataset, which is a collection of 12.5K middle and high school math competition problems from categories such as pre to intermediate algebra, number theory, pre-calculus, probability, and geometry. They found that for 38 of these problems, Codex was able to produce perfect formalizations of the problem statements as mathematical theorems in the language of the Isabelle theorem prover. That translates to a success rate of about 25%. However, among the remaining 112 problems, they document a total of 70 errors that are clearly syntactic, and a total of 98 errors that are possibly or likely semantic in nature. After manual sorting, Wu et al. Are able to exploit the 38 perfect formalizations to improve the downstream performance of the Liza neural theorem prover on the mini F2F dataset by 5.3%. And just to go through this table in a little more detail, the categories I'm referring to as clearly syntactic are the lower three above other, and the ones that I'm designating as possibly or likely semantic are the three above that. For the lower three, I say that because a missing definition or improper use of a function, these are things that can be immediately detected. Whereas it was not totally clear from their analysis whether by incomplete, ill-formed, or unclear prompt, they meant something that resulted in a syntax error or some other kind of error, but it was ambiguous. And something like failing to align definition or concepts seems like it clearly is a more insidious kind of error. It's not clearly outright wrong, the formalization that it came up with. And same with inconsistent or missing assumption. That's clearly a logical kind of mistake rather than a syntactic one. So language models are actually pretty good at approximating formal statements with no, better than nothing, at least. However, there are two different standards by which we judge the output of a language model on the task of formalization. We can ask, is it syntactically valid? Which basically means, can the theorem prover even read it? If it can't read it, then no one can even attempt to prove it correct. So syntactically invalid outputs can be discarded immediately, nearly free of charge. But we can also ask, is it semantically valid? There are lots of ways to interpret that question, but in our context, it's pretty straightforward. Does what they said in natural language describe the program that we're looking at? Wu et al.'s results suggest that on the second question, perhaps we shouldn't look at LLM's performance too rosily. Even on the much broader domain of general, mostly pre-college level mathematics, Codex is only right in both syntax and semantics 25% of the time. And while the breakdown of these results lacks some important details about how these failure modes overlap with each other, it's clear that language models don't make a particularly crisp distinction between syntactic and semantic correctness. There's a great variety of both of these errors, and they are the majority of cases. That doesn't seem like the best news. Wouldn't it be easier if language models were oracles? Yes, it would be much easier. But thankfully, we have other ways of finding proof. We just need some other mechanism by which we can validate the kinds of formal statements that language models can give us. As long as we have some other check, then it seems that we can roughly trust that the language models will track the correspondence between informal statements and those formal statements that we have certified are well-formed by other means. This is also supported by Wu et al.'s secondary result that language models succeeded at auto-informalization a much greater percentage of the time than they did at auto-formalization. So there is good reason to trust that language models make intuitive sense of informal statements with respect to some formal syntax. But we really should not expect them to know which of these statements are relevant or true in any particular context. So how can we establish some kind of verifiable relationship between formal and informal language? And can we do this without sacrificing the general applicability of language models to open domain conversation? Gordon et al. Gives us evidence that the answer is yes. The most prominent platforms for software verification today are based on a logic known as the calculus of inductive constructions, or the CIC. The CIC is a type system that is so expressive, type inference is undecidable. This is because its types can be used to encode non-trivial properties of programs. As a result, there's no general algorithm that can always say whether the characterization given by a type applies. There are still heuristic and incomplete methods for automating proof search, but they must necessarily tackle restricted problems, and they can fail. Gordon et al. Exploits the similarity between the structure of categorical grammars, a style of grammar that analogizes parsing to type inference, and the calculus of inductive constructions to turn a proof assistant into a parser using only standard features. And while I find the details of this fascinating, I think most people probably do not. So I'm going to largely skip them. I'll instead give you a feel for what Gordon et al. Accomplished by examining the most comprehensive case study. Gordon applies his method to a textbook, Verified Functional Algorithms by Andrew Appel, that happens to contain a number of exercises along with natural language descriptions. These exercises are theorems that the student has to prove about their implementations of various list operations, such as sorting and multi-set union. I personally find this chart a little difficult to read, but I've made my peace with it, so I'll try to help you all do so as well. Gordon presents 10 translations of theorems. In each of these rows, there's an original natural language annotation written by Andrew Appel, the author of the textbook, as well as the original theorem statement in the syntax of the theorem paper. He also presents the translated version created by his grammar, as well as the time it took to find this parse. The timing, I would say, should be treated as a little bit suspect. And I say that also because in practice, one could imagine essentially enumerating such a small grammar and then turning it into a constant time lookup. So there's really no reason that any of this really have to be dynamically done. Let's see. So we can just take a moment to appreciate some of the translations that he actually gives. And I would argue that while a lot of the translated language in this chart and the remaining 5 results are on this second slide, while they're not necessarily very elegant, I think a good example of inelegant to me was sort preserves contents and sorts. But it does have a verifiable meaning. And with some scrutiny and careful thought, we can also see that these examples are reasonable English that could be considered to have an unambiguous technical meaning. In a limited jargon-oriented context, these aren't inconceivable ways of describing these properties. Because of how Gordon et al. Implements this parsing mechanism as a specialization of type class inference, a feature already widely available in proof assistants based on the calculus of inductive constructions, providing these sorts of grammars for targeted sets of theorem statements is a trivial extension to existing proof engineering projects. Using Gordon et al.'s techniques, we can circumscribe fragments of natural language that are small enough to be fully formalized, but also large enough to capture a useful set of assertions within a targeted logical framework. This mechanism also need not interfere with how language models work at all. It does not have to play any role in determining how language is actually generated for it to be used. So we can rather leave the task of asking generally relevant and coherent questions to the language models themselves, with whatever implicit understanding of programs and programming that they already possess. Based on these papers' contributions, I would like to propose a specific way of instantiating the approach that I articulated at the beginning of this talk. So,
Sorry, can I interrupt one more first?
Yeah, go ahead.
We move on from this last one. Maybe they don't give this information, but is there any sign why sort preserves contents is so much faster than sort preserves contents and sorts?
I don't know that I have any terribly useful answer to that. They address timing at quite a bit of length in the paper itself, and they suggest that they're not really able to measure the time that was purely spent on the type class
Okay.
inference in the
Yeah.
first place. So there could be sort of some cold start things that are
Mhm.
adding a lot
All
of
right.
time to
Let
specific
me not worry
courses.
about the time then. Actually,
Yeah.
one other thing while I'm thinking of that. In mathematics, even within this
Mhm.
domain, we could imagine that sentence being ambiguous, right? It could mean that sort preserves contents and also sort sorts, or it could mean that sort preserves contents and also sort preserves sorts. Um, how
Oh,
do they get around this in their system?
when you say in the second sense, you're talking about like sort in sort of the categorical
Yeah,
sense, right?
people sometimes use the word
Yeah.
sort to mean something similar to type or kind.
Yeah, yeah. Well, so the basic answer is just that, well, so this is, I guess, a deeper tension in the paper, which is Gordon emphasizes, a great deal that there's so much linguistics literature on, combinatory categorical grammars specifically, and there's so much empirical evidence from scholars studying how we can sort of import so much language by default into the proof assistant by just imitating these grammars that have already been published. And while that is a nice thing to be able to say in general, I think that approach raises exactly the issue that you're bringing up, which is that if you have the grammar before you have the theorems it's grounded in, then what have you really accomplished? Basically, in my view, the whole value of this approach is that it relates natural language to theorems. And so as long as the user is in on the contract, that they're trying to talk about something very specific enough that they're sort of willing to concede that there have to be specific ways to say things that are true or false, then if you mold the grammar around the domain of theorems, then you don't have to worry about the more general problem of, is this a reasonable way of parsing lots of natural language? And
Mhm.
they discuss that idea that just in the linguistics literature, they're fine with undergeneration from a grammar. They're fine if the grammar can't parse everything that is legal in the natural language, but they try to not have it misinterpret, and they try to not have it overgenerate, say that things are parsable, which don't make any sense in the natural language. And so this approach is very much sort of, yeah, based on the idea that you would just encode one way to talk about this small set of truths. And it's definitely not the only things that those sentences could mean in natural language, nor is it even necessarily the only way that you could put these theorems into something that's natural language like.
Okay, thanks.
Yeah, thank you. Um, so, oh, uh, yeah, so actually I have to go back to nearly the beginning at this point. Yes. So we start again with the utterly unapproachable big picture. Um, Previously, I described that we break this down by looking at specific regions and proposing under specifications of the code in those regions. Well, how exactly does that occur? Seems a bit tedious, right? Wrong, because I'm not the one doing it. A conversational AI assistant is the one doing it. I can be skimming through this code base at the speed of scroll, just chatting away. And what's happening in the background? Two things, potentially. One, the language model is chatting with me, making me feel heard, whether or not it has any earthly idea what I'm referring to. And two, the language I'm using is being skimmed by that parser implemented in the proof assistant for subsequences of tokens that can be parsed to some kind of formal statement about what various regions of the code are accomplishing. When I say something that happens to have a formal interpretation, this information is paired with knowledge from the IDE, the user interface, of what code I happen to be looking at in order to determine a region for which the condition parsed from my speech may indeed be an appropriate under specification. Whenever I reach the point of having provided some under specification of all parts of a larger segment of code, so assuming this is exhaustive, my conversational AI assistant can then report to me whether these descriptions are collectively an over specification relative to each other, and if so, how. If that check succeeds, then I have a guarantee that I have at least accurately captured some of the behavior of this underlying code. I could then design any concrete syntax, any kind of pseudocode, essentially, to represent higher level abstract steps that achieve P1, P2, and P3 one by one, exactly in that order. I could then choose to look at that abstracted syntax rather than the original low-level syntax, and know that what I was looking at was the results of a limited kind of verified decompilation. This kind of capability to look at a code base alongside a programmer and to help them pick out the narrow but verifiable description that captures what they understood and sought to observe about that code. That capability suggests a vastly more practical paradigm for grounding natural language statements in actual programmatic behavior than the alternative offered by tools like Copilot. By forcing programmers to rely on it to guess their intentions, Copilot confiscates any control programmers exerted over the generative process itself, but leaves them with the same burden they had before to assert ownership and responsibility over the logic of the result that has been produced. I hope that today I have managed to sketch a compelling alternative. Tim. Thanks. Oh, perfect. Yeah.
Okay, so now we've reached the questions.
Yes. Yeah.
I don't know how you want to, William is online, we're in person.
True. Well, why don't we do in person first and then switch to online if it doesn't disadvantage anyone too much. Yeah.
Yeah, I mean, I don't have that many questions. Let's see. So one thing, I guess I think it was the second paper, right, where they had like the timing information in that table.
Oh,
Yeah.
yes.
A little bit confused why they included that timing.
Well, so I think I can contextualize that a little bit. The reason that they do that is basically that they're kind of misusing a system for something that it's not strictly meant to do in using a proof assistant for parsing. Type classes are a mechanism popularized in functional languages. They're basically like an interface. It's like an interface in Java says, here's multiple ways you can implement the class. A type class says, here's the trait of being printable or being equality comparable or something like that. And here's a broader type, and then other things can implement that type more specifically. That then requires that the compiler basically figure out which specific equality, which specific printing function was actually being referred to in any particular context, because you maybe just say print or CMP, and in your code, you just write that, but underneath the hood, it's being swapped for something else. And basically what Gordon et al. Does is treat actual English sentences as if they are just another way of writing the type that is the theorem. In the same way that you could say, I'm printing this object and I look up in the class definition what it means to print that thing. And so it's an optimized mechanism, but it's definitely conceivable that it would be impractically slow for this purpose. One should at least account for the possibility a priori that it's not actually, it doesn't run intolerable time or something, because it's not what it was strictly meant for. Yeah.
And then my other question, I guess, and you kind of described this in the write-up, but I guess just in short form, perhaps. So I guess like these free papers kind of lead up, right, to like what you're planning to do next, basically, like the basis for that. So, could you just summarize, like, I guess, what is your big, like, what is the overarching takeaway from this, and like, where, I guess, how does this set you up going forward for your research?
Sure. Thank you for that question, I think. Let's see. I think the way that what it sets up is, from the proof engineering side, it isolates some ways that we might be able to build proof automation that happens to answer questions that people already know how to talk about in a natural language oriented kind of way. And then from the natural language side, it gives us some way to potentially let natural language models participate in conversations where they actually make provable claims about something. And that second direction could have very, very broad and exciting implications in the very long run. But I suppose in the narrower view, language models have made it, trivial to compose text. And for a long time, formal methods approaches have made it so that if you're willing to sit down and do it, then it's very ergonomic to prove why code works. So on one side, we have something that's sort of only limited by the speed of a GPU. And on the other side, we have something that's only limited by the speed at which humans can actually figure out real logic problems. And if we could bring those two together in some way, if formal methods could benefit from the speed improvement in just producing characters that are in some way coherent, in some way drawn from a distribution of reasonable language, then there might be a huge amount of speed up to be gained. It's just that these two systems make very opposite assumptions, and it's all kind of in how do we create sort of the narrow bottleneck that they have to communicate through.
Yeah, in some slide, I see you mentioned some like two sample tests, right?
Oh yeah,
What's that? Why do you do that?
I just mention it because well, honestly, I did a run through of my presentation, and some people who are not statisticians said, could you please explain all these tests? So I decided I should be able to. But specifically, I don't think that's quite the slide. In this specific context, the reason that they use that test is because essentially you have two groups and they completed programming. There are a bunch of times for how long it took them to complete different tasks. And you basically want to say, does it seem like the mean of the differences between the times that it took programmers to complete each respective task? Does it seem like those means are centered on a number less than 0, greater than 0, or 0? And you're trying to disprove the null hypothesis that the means are centered on 0, which would mean if the means of the differences are centered on 0, that means there's no real difference in aggregate in the times it takes to complete the task. So the Wilcoxon two-sample test is a kind of, it's similar to the signed rank test.
This is
Yeah.
the common you use in this field, right? Like this approach is the common use.
Well, I'm sure to statisticians it's very run-of-the-mill, but yeah, but I had to look it up. So yeah. I guess, William, do you have any other questions right now? And then I guess if there are any audience questions.
Yeah, I'm happy to let audience ask questions first. I don't have anything immediately.
Okay. Well, there's just two in-person audience members. Anything you guys were wondering?
You already answered one of my questions. It was about basically LLMs speeding up the verification process.
Yeah.
But I have an additional question, and that would be like, let's say if we don't know how to solve a problem, like user doesn't know, or even a programmer doesn't know how to get started with the problem. We might come up with some solutions, and then we hit some walls.
Yeah.
And then we figure out, okay, this is the right way to do it. So would like LLMs in the future help users to do that who are not programmers?
Yeah, well, I guess what one other way you could maybe reframe where this is trying to go is, can you try to reason something through with a language model? And when you're making enough sense for the theorem prover to turn that into an actual proof, can it just happen in the background? And if it's not, can you just keep talking? And so I guess sort of the idea is some subset of what language models say could sort of through the interpolation of the specific proof automation framework, plus this grammar that says these particular wordings correspond to provable or disprovable statements, that there's sort of some subset of the reasoning that occurs in normal natural language conversation that can be done in parallel in a formal manner. And can we basically set up both of these systems so they can both be working on that at once without you having to only talk to the language model about things that you know are provable. You can basically go off the beaten track of saying things that you can prove at any moment, and it doesn't impede the conversation. That's sort of the degree of adaptation to that problem that this is proposing. But of course, ultimately, if one doesn't know how to say anything that's sort of logically relevant at all, then this doesn't address that challenge. Yeah, any online participants have questions? I'll take that as a no.